So now let's see how to generate a random forest with SAS Studio. Again, I'm going to use the Wave 1 Ad Health survey that I've managed for the purpose of growing decision trees. You'll recall that there are several variables. Again, we'll define the response or target variable, regular smoking, based on answers to the question, have you ever smoked cigarettes regularly? That is, at least one cigarette every day for 30 days. The candidate explanatory variables include gender, race, alcohol, marijuana, cocaine, or inhalant use, availability of cigarettes in the home, whether or not either parent was on public assistance, any experience with being expelled from school, age, alcohol problems, deviance, violence, depression, self-esteem, parental presence, activities with parents, family and school connectedness, and grade point average. Following the libname statement and data step, which I am using to call in this data set called Tree Ad Health, I will include proc HP forest. Next, I name my response or target variable treg1 and indicate with a / and the level option that it is a categorical variable by including the word nominal following the equal sign. Categorical, quantitative, and even ordinal variables for my random forest need to be included in separate input statements. Here I include my categorical explanatory variables followed by the word input and end the statement with a / level option, and the word nominal following the equal sign. Then a second input statement for my quantitative explanatory variables, indicating that they are on an interval scale. As always, all statements are ended with a semicolon. Finally, I end my program with a run statement. So let's run the program and take a look at the output. We can see in the model information section that variables to try is equal to 5, indicating that a random selection of 5 explanatory variables was selected to test each possible split for each node in each tree within the forest. By default, SAS will grow 100 trees and select 60% of the sample when performing the bagging process. That is, the in-bag fraction. The prune fraction specifies the fraction of training observations that are available for pruning a split. The value can be any number from 0 to 1, although a number close to 1 would leave little to grow the tree. The default value is 0. In other words, the default value is not to prune. Leaf size specifies the smallest number of training observations that a new branch can have. The default value is 1. The split criteria used in HP Forest is the Gini index. In terms of missing data, if the value of our target or response variable is missing, the observation is excluded from the model. If the value of an explanatory variable is missing, proc HP Forest uses the missing value as a legitimate value by default. Notice too that the number of observations read from my data set was 6,504, while the number of observations used was 6,500. Within the baseline fit statistics output, you can see that the misclassification rate of the random forest is displayed. Here we see that the forest misclassified 19.8% of the sample, suggesting that the forest correctly classified 80.2% of the sample. Now I'll show the first 10 and last 10 observations of the fit statistics table. Proc HP Forest computes fit statistics for a sequence of forests that have an increasing number of trees. As the number of trees increases, the fit statistics usually improve, that is, decrease, at first, and then they level off and fluctuate in a small range. Forest models provide an alternative estimate of average square error and misclassification rate, called the out-of-bag or OOB estimate. The OOB estimate is a convenient substitute for an estimate that is based on test data and is a less biased estimate of how the model will perform on future data. We end up with near-perfect prediction in the training samples as the number of trees grown gets closer to 100. When those same models are tested on the out-of-bag sample, the misclassification rate is around 16%. The final table in our output represents arguably the largest contribution of random forests, specifically the variable importance rankings. The number of rules column shows the number of splitting rules that use a variable. Each measure is computed twice, once on training data and once on the out-of-bag data. As with fit statistics, the out-of-bag estimates are less biased. The rows are sorted by the out-of-bag Gini measure, or OOB Gini measure. The variables are listed from highest importance to lowest importance in predicting regular smoking. In this way, random forests are sometimes used as a data reduction technique, where variables are chosen in terms of their importance to be included in regression and other types of future statistical models. Here we see that some of the most important variables in predicting regular smoking include marijuana use, alcohol use, race, cigarette availability in the home, cocaine use, deviant behavior, etc. To summarize, like decision trees, random forests are a type of data mining algorithm that can select from among a large number of variables those that are most important in determining the target or response variable to be explained. Also, like decision trees, the target variable in a random forest can be categorical or quantitative, and the group of explanatory variables can be categorical or quantitative or any combination. Unlike decision trees, however, the results of random forests generalize well to new data, since the strongest signals are able to emerge through the growing of many trees. Further, small changes in the data do not impact the results of random forests. In my opinion, the main weakness of random forests is simply that the results are somewhat less satisfying, since no trees are actually interpreted. Instead, the forest of trees is used to rank the importance of variables in predicting the target. Thus, we get a sense of the most important predictive variables, but not their relationship to one another.